So here we are, back again with another video for our series Turing Complete. This time we are going to start with immediate values. Let's see. Sometimes it is useful to load a value directly from the program instead of the registers. This is called loading an immediate value. In the like architecture, we signal when we want to do this directly in the opcode. We can do that in the following way. When the 8th bit of the opcode is green, use argument 1 as an immediate value instead of a register address. When the 7th bit of the opcode is green, use argument 2 as an immediate value instead of a register. Wait, let us read the full instruction. Yeah, that makes total sense, right? The only thing that we get is a graphic that is showing us what to do. All right. So I mean, we can just do it like this. The 8th bit, right? So that would mean this one means immediate argument 2, and the 7th bit means immediate argument 2, immediate argument 1. How do we do this? Instead of a register address. So I guess that would only be relevant in the case that we want to perform an operation, right? Right. Let us read the instruction again. When the 8th bit of the opcode is green, use 1 as an argument. Use argument 1 as an immediate value instead of a register address. When the 7th bit of the opcode is green, immediate value instead of a register address. Alright, so in theory, that would mean in case we copy, we wouldn't use the ALU, but this is not going to be relevant for now. So we have this. This. And this. And you would have to sit before the ALU instead of behind the ALU. This is going to be of relevance when we start to want to copy. U, and once more. 8th bit, argument 1. U are the 8th bit, argument 1 is the yellow one. 7th bit corresponds to the... But instead of a switch, we actually want to use a mux. I just realized. So I guess this is how this would have to look like. And the reason for that is no, we would take U instead, right? Now it's going to get a little bit messier. But hey, still kinda fine. I guess that will work. Yes, it does. Because the mux decides which one we are going to use. Either the one that is given to us by our big register, or the one that we get directly from the program onwards. Conditionals. Add if statements to a circuit. For if statements, the second argument, the two arguments are compared, and if the condition is true, the counter is set to a jump address. Previous instructions had the 4 bytes represent opcode argument 1 and results opcode argument 1 jump address. In addition to the previous opcodes, add if equal, if not equal, if less or equal, greater or equal. Wait, the previous opcodes? Add if statements to a circuit. For the if statements, the two arguments are compared, and if the condition is true, the counter is set to a jump address. The previous instructions that the 4 bytes represent. In addition to previous opcodes. Alright. So that would mean that all the previous opcodes would be all our logical and mathematical opcodes. Answer and less. But why? First of all, we're going to take a screenshot of this. I mean, I guess the easiest variant would be to modify our ALU, but we could create a condition component as well. Let us think about this for a second. If we use our ALU, it's going to be compact. It's going to be not only compact, it is also going to be a little bit more complicated as well. At least the ALU component is going to get a little bit more complicated. Let us enter the component factory and build a conditional component for now. On the other hand, now that I'm having a look at the ALU, right? Like the easiest variant. No, it is way better too. Since we have this deactivation bit for the ALU, which is going to make it... This is going to be great. Because right, we will have to deactivate the ALU in case we're going to use the conditional component. The reason for that is that we don't want it to write to anything. And the problem is as well, we have register 0, right? And register 0 is going to be triggered so we are going to write a 0 into register 0 if we aren't careful about how we manage this. So I mean 32 can just be used to deactivate the ALU. But I actually really like the idea of a stronger ALU. And the reason for that is we're going to be able to... No, it doesn't make sense. Actually, it doesn't make sense. Because the way the level wants us to build this thing is that we give it a jump address. Like straightforward a jump address. Just a number. That means that we are going to have to use this third argument, which is usually the result address, and write it to the counter. I'm going to use a mux first of all. Let us get building. This is going to produce some results, and this is going to be great. So U32 are our opcode that decides that we are going to use U for our counter. Input 2. Yes. But this is only true if the condition is met. Where's this blue? Because it's a result address. Yeah, that makes sense. I mean, we can also use this one. Make U point to 0. I actually really like the idea. No, not to 0, but to 8 actually. It's a byte constant. This solves two problems at once, right? I'm going to use a mux here. Going to use a mux here. I hope that eight actually is the counter address. We can have a look. So this would be the 7th. We cannot have a look. Great. Anyway, I'll just trust and the fact that I trust in myself, that I haven't made a mistake, or rather remember it correctly. So you're going to point to our counter. It's just going to look better. Maybe we can pull you down as well. Maybe for you go like this, actually. To need you later, but for now not. So far everything is fine. The only problem that we are having is that we only want to feed you Still gonna have to use a logic gate right here. There's no way around it. Because in case, like in general, you would be active, right? If the condition is not met, we need a signal that is. Maybe we can just go with NAND instead. That is not only going to be the condition is met. If the condition is not met. No. No. Okay, let us build the condition component first. Or still, do we build it into our ALU? We will build it into our ALU. First of all, let's pull out our screenshot. See how this is supposed to be done. If equal, we're going to do it like this. No. Because it will enable us to not have to build a separate MUX. I think this is a very very nice way of doing it. Alright, equals. We already have these, right? Equal, not equal. They said we were supposed to use unsigned, right? So this is what we need for our thingy. Equal, not equal. This is unsigned less, right? Unsigned less. So this will be greater. Basically. We can build the logic in a way that, wait, argument 2 is yellow. No, green. It's going to be the most compact way of building it. No, it's not. Because we can do it like this. We don't even have to use this. Because from this point on, maybe we should use a separate color for conditionals. From that point on, we can build the rest in gates. Alright. But we are going to use switches. So, equal, not equal. We can directly connect this. No, we're going to do it like this. Equal, not equal. Less. Less or equal. Greater. Greater or equal. One, two, three, four, five, six. And these are 6 as well. I'm still wondering why we would use unsigned less. I guess this is what the level wants. So this is less, this is equal. This is... no, this is less. This is greater. This is greater equal. Now we will have to add a component that lets us output our signal. Maybe we can put it here. Kinda like how this looks. The thing is, if we are in this mode, right, that would mean we would be in conditional mode. In conditional mode, actually wait. Doesn't fit anymore. Now it fits again. Okay, maybe we put the button here. Instead, the output. Right? Name it conditional. So what we were going to check is, do we have to? No, we don't even have to care. See, we don't even have to care about this whole stuff. This won't matter at all. It's just that. It's gonna be like this. 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 I'm going to definitely use a different color for conditionals. 1, 2, 3, 4, 5, 6. But you only output anything if this one is online. So can we use yes, we can use a switched output. This is the perfect solution. Still, once more, name it cont. So we wouldn't deactivate you, right? So now the question becomes, we only write, let us change the color of this to our conditional color. That we in case we're in conditional mode, Because we would have to make sure that whenever we activate this, which we do by using this mux, maybe this mux is the problem. Maybe this mux is actually the problem, because we wouldn't have to. Like, if this is not 8, right? That has to be 8. So we would have to make, because we have to make sure that you do not address and register. We could send 0. We can use a mux. Or is that a switch? Because this switch could be used to deactivate you. Now we are going to use an OR. Because first of all, the switch deactivates. This condition, which is basically going to be met the moment we set you to counter and have it rely on you instead. And you're already built in a way that you can only light up when the condition bit is online. So this will solve the level. It does not. If register 0 is equal to register 1, jump to 24. Okay, why doesn't it work? The result is 0. But why? We feed 24. Does it make it past the switch? Why? Why doesn't it make it past the switch? Like, the switch should be active, right? You are getting an 8. So 8 is not the correct address? Yes, because you how? Okay, first of all, let us see. You are the counter address, right? No, you are not. But what then is exactly the counter address? 8, 9. We are switching through these. 6. Yes, this is it. So this will solve the level. Jump to 0. Is not equal. Oh, you're supposed to deactivate the switch. Okay, what is the next problem? If wedge 0 is smaller than wedge 1, jump to 104. So is it the case? First of all, no, 0, 0. This is wedge 0, this is wedge 1. Both are 0. So we don't jump, but the condition is met. So that means the condition is met even though it shouldn't be met. Is less. No, it's greater. This is if it's greater. 36. Let us see how this looks. Opcode is 36. Greater. Oh, because they cannot be equal. Of course. If it is not... Oh, this is... Oops. I've built this wrong, actually. Okay, the first part was correct. If it is equal, if it is not equal. See, if it is less. This is less. This is definitely true. So, but if it is not less, right? It is greater or equal. So if it is not equal, and it is greater or equal, only then is it greater. How about less? Because less is really built with an OR. If it is less or equal, less or equal, greater, greater or equal, now. Now is the time to solve this level. Congratulations, you finished the lag computer. Great. Here we have it. Wonderful, right? And you see, we had options. Sorry for the fading light, by the way. Congratulations, you finished the lag computer. See, we had options. We could have built a separate conditional component as we did an overture, we decided to build our condition into our lag, into our ALU, and this is how we solved it. Yeah, actually, I don't know if you're actually playing this game and you make solutions. I would love to see yours. Definitely. Yes, this was it for today. This was IP42. Hope you had a great time. Goodbye, and I hope to see you again.